minor closed classes of graphs.
Yeah, excellent. First of all, thank you very much for inviting me, and thanks a lot to the organizing committee for giving me the opportunity to present a part of my PhD thesis here this afternoon. And if you don't really know what these things are, like, don't be afraid. I'm going to explain them, and I'll give the definitions and try to be as clear as possible. So I'm a graph theorist. I'm doing combinatorics. I work in discrete mathematics. And what's the object that I'm interested in? Well, they are graphs. And a graph is just an ordered pair of a set that's called the vertices and an edge set, where the edge set is actually just an ordered tuple of the vertex set. And in my graph, or here in my talks, all my graphs are going to be labeled. So you should think of that set as just being the integers 1 up to n. And then I need a couple of kind of standard terms that are actually, I hope, fairly simple. So I need to know, what does connected mean? Well, connected just means take your favorite graph, and between any 2 points you have there, between any 2 vertices, you can find a path. And then a component is just a maximal connected subgraph. I'll give an example in a second. And then what is a class of graphs? Well, a class of graphs is, at least here in my talk, it's a little bit of simplification, is a set of label graphs that are closed under relabeling. So obviously, because we have labels, somehow you need to know when are 2 graphs equivalent and everything. Obviously, graph theorists are concerned about that, but here we just oversimplify things and just assume, well, they are labeled, but all this relabeling business and isomorphisms and things like that, we just not care. Okay, simple example. Here, if these 2 things are a graph, then each of these connected things are components, okay? So this is a graph consisting of 2 connected components. What's my model? What's the kind of questions I'm going to address? Well, graph theory has been around for more than a century now, and mainly we can ask many types of questions, and especially people have been concerned about random models, so kind of doing probability on graphs or with graphs. And the model I'm going to talk about today is the so-called uniform model. So suppose I'm given a class of graphs, somehow I defined them, and then I want to ask, what's the properties of a typical graph on n vertices? And what's a typical graph? Well, it's a graph that's sampled uniformly at random from the set of all graphs on n vertices. So I'm not going to, if you're familiar a little bit with graph theory, don't think about the Erdős-Rényi model, but really just take a box, have all the graphs on n vertices in it, pick one uniformly at random, and look what happens. What are the properties that we're concerned about here? Well, first of all, I want to enumerate this class. So I'm doing a little bit of enumeration of combinatorics. But here in my talk, I'm going to address primarily the probability that my random graph is connected. So depending on what type of class I pick here, obviously, it's not clear what happens. Whether that probability exists, whether, if I let n tend to infinity, whether that exists, whether it's 0, whether it's a constant, not clear. And then I'm going to study the number of components. So, I mean, here this is a uniform or this is a random model. So I'm going to get a distribution of the number of components. And I want to address that for different types of classes of graphs. And obviously, you can ask many more questions. You can ask, what's kind of the expected size of the largest component? Are you likely to have a lot of edges? All these sorts of things. And just quickly to recap, so over the whole talk, that's going to be a class of graphs, script A. If I want to talk about the number of graphs on n vertices, so the cardinality of that set on n vertices, that's going to be just capital N. And sometimes I need to talk about the connected substructures in my class. That's C. And then I will focus on that a little bit later on, is I need to know something about A, or if I want to say something about A, I say A is decomposable if A is basically made up of connected components. So a graph is in A if and only if every component is in A. Example. Okay. My favorite class of graphs are forests. I really like forests. What's a forest in graph theory? Well, a forest is just a graph without a cycle. So here you see a big forest, doesn't contain any cycles. And as in real life, kind of, what is a forest made of? Well, it's made of trees. So a connected forest, a connected graph without a cycle, is a tree. So this graph here is a random forest consisting of 2 trees. You have here this one tree, and then here this little thing over there. Okay, Now I told you we want to see if I have a box with all forests on n vertices, I pick one uniformly at random, how many components does it have? Is it going to be connected? I tell you that this is such a forest. I sampled it uniformly at random. I'm not going to talk about methods how to do that. Just believe me for a second that this is actually randomly sampled. For people who are really interested in that, that's done via Boltzmann sampling. And here you can see, apparently I'm quite likely to get like a big tree and just a tiny bit. Is that typical? Well, quite early on, Rainey proved, yes, this is actually typical. But first of all, Rainey proved we can actually enumerate forests. This is a very old result due to Cayley that basically says if we want to just count trees, so graphs without a cycle on n vertices, we can do that here. And this is then just applying Stirling's formula to it. So, and I'll explain in a second why I did that. And here we're enumerating forests. And kind of the crucial thing to observe, if you compare the number of forests to the number of trees, they only differ by a constant. So we barely have more forests than we have trees. That's actually quite, when I saw that first, that's actually quite surprising. I don't, like, forests are connected, are disconnected trees, or maybe disconnected trees, but somehow we barely have more disconnected structures than we have connected structures. Which then leads to the following result. If I'm interested in the number of components, if I pick a random forest, how many components this is going to have, I have a Poisson law, a discrete law, and I even know the parameter. It's a parameter of half. Here is the definition of the Poisson law. And in particular, I told you that I'm interested in the probability that something is connected. So the probability that my random graph, my random forest is actually connected, so that it is actually a tree, tends to a constant. It tends to 1 over square root e. Okay. That's basically the setup. What's one of the features that this class of forests has? Well, one of the features is it's actually minor closed. Now let's define what is a minor. A minor of a graph is a certain type of subgraph that's obtained from my original graph by contracting edges, deleting edges, and deleting isolated vertices. And then I call a set of graphs minor closed if any minor of a graph that's in A remains in A. So kind of a typical mathematical notion. And then there's this famous Robertson and Seymour theorem, which was proved over the course of 20 years, and which is probably, I'd say, one of the most important theorems in my field. And it actually states that a class of minor closed classes of graphs can be characterized completely by its finite list of excluded minors. Brief word, why are minor closed classes in general interesting? Well, I was talking about trees, but generally in computer science, it turns out that many algorithms kind of work well on certain types of minor closed classes of graphs where you can forbid a certain minor. So algorithms work well if I can say I exclude x, y, z. The only important consequence of that theorem here is basically that if I want to characterize my minor closed class of graphs, it suffices that I give you the list of the minimum forbidden minors, and therefore the whole thing actually makes sense. I mean, I can somehow talk about these things. And an easy example, my class of forests, my class that do not contain a cycle, well, I can characterize them as the graphs that are minor closed and that do not contain a triangle. If you think about it, if I go back and show you that pretty picture, here, no matter how you contract an edge here, or how you delete an edge, or how you delete an isolated vertex or whatever, you can never create a triangle. Okay, so we're interested in that. What's the way to analyze these things? The way to analyze these things is via generating function. So now complex analysis comes into play, and therefore I'm particularly grateful that I'm here, because I've never spoken to anyone within the complex analysis group about what I'm actually doing. Okay, a generating function, you probably all know what a probability generating function is, and in combinatorics it's actually a similar object. So suppose we have our label combinatorial class, say a class of graphs, say the class of forests, whatever. That's the number of structures of size n. And then I define this object, so this number of graphs on n vertices divided by n factorial times my variable z to the n as my generating function. And then what's the idea of analytic combinatorics? Well, the idea is now somehow we can easily get access to these generating functions, not necessarily to the coefficients, but then we basically have an analytic object and we can do complex analysis on it, and we can therefore deduce something about the combinatorial properties of my class. Sounds very vague. Maybe this will a little bit clarify the situation. So suppose I have a generating function. So for the moment it's just a power series with natural coefficient or with non-negative coefficients. And then most likely, probably the complex analysis people will kill me here, but most likely it will look like this. So if I want to have the coefficient of z to the n out of my generating function, it will look like that. So it will have an exponential part and a sub-exponential factor. Okay. What's the first principle of kind of my analytic combinatorics? Well, the first thing is basically the location of the function singularities will determine the exponential growth. Well, that's something you all know, because you kind of know that from your first analysis class, because that's basically the radius of convergence. If I know the radius of convergence, I know this part. And the second principle is, if I want to get access to the sub-exponential factor, well, that's determined by the nature of the function singularity. So depending how violently it grows around its singularity, I can somehow get this sub-exponential factor. And then obviously, you can also easily think, one can probably kind of generalize these things to more than just one variable, and like that you can get limit laws. So if I say want to know how many components, how many graphs are there on n vertices with k components or something, I can decode that from that. But I'm not going to do that here. Okay. And then from here on onwards, I'll talk about dominant singularities. And what I mean here, is just, in our case, that's basically the first time, or that's basically my radius of convergence, because the dominant singularities for our purposes, here because we have generating functions, will be on the real line. Okay, that's all fine, that's all good, but it remains the question, it still means I have a combinatorial class and I need to get the generating function. Is that possible? And yes, it is possible, because we have something that's called the symbolic method. And that's basically, the idea is simple. We have constructions in discrete mathematics that appear all the time, that we build cycles, that we exchange things, that we substitute in things, and we can actually find a correspondence to operating on generating functions. We can translate that into complex analysis. An example is, we should actually switch to that thing here. Suppose we have a decomposable class. So I told you that's a class where I can build all my structures by just taking combinations of connected structures. So I take forests, they're all made up of trees. So take any possible combination of trees, then you'll get a forest. Okay? Yep. That's basically what I've written here. Any possible combination. 1 tree, 2 trees, 3 trees, whatever. And that translates, in terms of the generating function, that translates if the generating function of my connected structures is ∇1, the generating function of all the structures is just exponential functions of the connected function. And obviously, then you already observed the first thing, i.e. that the radius of convergence of this guy and this guy is going to be the same. And therefore, like the exponential growth between a decomposable class and its connected structures, that's going to be the same. So they're only going to differ in the sub-exponential part. Now I'm going to quickly say what's known in the literature about minor closed classes of graphs. Well, first of all, we're going to do the two-connected case. First of all, what's two-connected? Two-connected means I have a graph, and I have to delete at least 2 vertices in order to disconnect the graph. This graph is not two-connected. Take that apart, and it falls apart. This graph is clearly two-connected. Take any 2 vertices, delete them, you'll still have a connected bit. And I tell you that the generating function, in this case, at the radius of convergence, at the boundary, will actually converge. You probably know from your first analysis class, well, if we have radius of convergence and we're strictly less than the radius of convergence, we converge. If we are bigger, we diverge. And what happens precisely at the radius of convergence, well, depends on the situation. But I tell you, for these special functions, associated with these combinatorial objects, well, it converges. And that's actually a theorem that has been around not for many years. It has been improved. And it states, let A be a minor closed class of graphs. Suppose that the excluded bits are all 2 connected. Then first of all, we can replace in our radius of convergence the lim sup by the lim. So we somehow behave rather smoothly. And the number of components is going to be a shifted Poisson thing. Shifted Poisson law, so kind of same behavior that we observed for trees. And we can even bound what happened or how big the parameter is going to be. And then obviously, if you want to know something about the proof, well, it's super, super crucial that you prove that this thing exists. That's not obvious. And even you need a little bit more than this growth constant thing. You need that your connected structures are smooth. So this is basically the ratio test. The ratio test for your generating function has to work. And what happens if they're not connected? Well, that's basically what I've been working on with Mireille. Okay. First of all is we have, like my talk will now be very much examples. Like I don't really go into the details. I won't really explain the proofs. It's just more pictures and kind of different scenarios what could happen. So first of all, there are some classes of graphs where we still have the same type of behavior that we had in the 2 connected case. So we're still going to converge at the dominant singularity. And it's the following. So suppose we have a decomposable minor closed class of graphs, and we contain all trees. All trees are in it. But we exclude, for some reason, we exclude the k-spoon for fixed k. K is an integer, and the k-spoon is just this graph. So it's the triangle, and you put on this handle, and you increase the handle. And then the first thing is basically the connected structures look like trees. You can't have many more than trees. Asymptotically, that's precisely trees. But now, that might be not too surprising, but now actually all the structures, so connected and disconnected, they behave also like forests. So you just have a constant, that's the generating function of A evaluated at 1 over E times the connected structures. And the number of components of this class for any k will be a shifted Poisson law. But now we're going to be, here this parameter is actually for minor closed classes of graphs where the excluded minors were 2 connected, we had bigger or equal, and now we're less or equal. So somehow a little bit of different behavior, but not quite. Okay, sometimes we're going to have that. Now you can ask me, does something like that exist? And I tell you, well, here it exists. So if you exclude these 3 minors, for any k, you'll have a class of graphs that have this type of behavior. Next question. Good. What happens if I now increase k? Well, for every fixed k, I have that, but in the limiting case, what happens? Here's a picture of the limiting case. Basically, it means we're only excluding these 2 minors. That's obviously something you have to prove, but you can prove. Limiting case is basically you get rid of that, and you just have that. And here's a graph. Well, out of a sudden, you have a couple of disconnected blobs, right? You have a couple of components. You get 1, 2, 3, 4. Is that typical behavior, or is it not? And I tell you, well, it sort of is, and you can already observe that from the generating function. So that's kind of the dominant singularity of the connected structures of these type of structures. They will behave like 1 over log, and clearly, I mean, this part will diverge, right? If you plug in rho here, you have 1 minus 1, 1 over log, 1 minus 1, log over 0, log of 0. I mean, that's clearly, somehow you got a problem. So what happens? Well, first of all, the connected structures, so you still have the exponential part, sub-exponential part, and then this part. And you still have somehow the same behavior for the disconnected structures. But now you got the problem that you don't have a constant times more connected structures in this case. So here you have e to the root e to the n in both cases, but here you have 1 over 4n, and here you get n to the minus 3 over 4. So clearly there are far more structures here than there are there, and that's reflected in the component law. You get a normal distribution and about log n component. Can we go more violent? Well, yes, we can. 1 over square root is the next example. I'm quickly going to skip through it. Same thing here. You get e to the n divided by 1 over root n. And here, actually, e to the n divided by n to the 3 over 2. So definitely more structures here. Times this kind of strange factor, e to the 1 over 3. That's actually quite crucial, because that actually means that there are even more disconnected structures than in the previous case. And that's also reflected in the limit law. It's a typical graph. We have a limit law that's also normal, but now actually the number of components we expect is about 1 over 3. And I skip the proof. Ah, yeah, that's the generating function we have to analyze. So then it gets technical and it gets messy, because somehow you need to have analytic methods providing that you can extract coefficients from something like that, or even exponential of something like that, where this is where actually the t is a function that's just implicitly given. So that are kind of like technical bits we're facing. But it can go even more wrong than that. So we are coming from 1 over square root now to a simple pole, and that's for forests of path. So forests of path are just things that are made of path. That's a typical one, and you can already see you get a lot of components. And for the caterpillars, so a caterpillar is basically a path and then a lot of legs. And also for that, you get a lot of components. And that's then reflected in their limit law, so we expect about root n components here. Well, and basically, what's left to do? I mean, there's a lot of open questions in the area. Like, there are many people working on that, but still there are tons and tons of open questions. And they're sort of more graph theoretical ones, dealing basically with whether we have this smooth type of behavior, and then the generating function questions. And basically, I mean, the main question is still open, which is basically saying, if I give you a class of graphs, can you tell me what type of or what's the dominant singularity? And I have something about that. And then also, I mean, once I have that, if I have a dominant singularity, can I then get a complete classification? Can I immediately get the limit law? Can I immediately get the law for the largest component? That's still, yeah, kind of like that. And then, yeah, that's basically kind of, I talked you through excluded minors here. I didn't do that. And then these 3 lines. Thank you very much.
There's some more questions. Okay, yeah.
So is there any progress on this open problems that you described?
On these ones?
Yeah.
Yeah, I mean, they were first stated, I think, in like 2005, 2006. And basically, we both know them when we exclude 2 connected minors. So when I showed you the big theorem, I mean, in these cases, it's done. But in a certain sense, these cases are very simple because we converge at the radius of convergence. So we have a very kind of specific, like a very, very well-behaved class. And for all these classes that I've talked you through afterwards, it's completely open. And the people in the field really, I mean, even the experts, they don't have any idea. Therefore, it would be very, very handy if some complex analysis person is actually keen, because we have some sort of analytic properties for a couple of cases, but we don't really know how to translate it in a statement of fact.
What are the simplest cases where this is open?
Simplest cases, I mean, take any non-2 connected minor that you like. And like the problem is basically like either, I mean, it's a pretty trivial problem, because either I have a complete estimation, so I can precisely tell you the number, or I don't know anything. But this kind of intermediate results, they are missing.
I was wondering if you've been using, because you have all these pictures, have you been using numerical simulations to make conjectures?
Not actually to make conjectures. That's actually the funny part.
Useful sets of minors to exclude.
Not even that. Like, the problem is a little bit, like, you can draw these pictures and you can make these simulations once you know the generating function. So once I have that, I can draw pictures. But once I have that, I can also do the full analysis. So it's a little bit like, for some reason, numerical methods seem to not kind of be the appropriate mean to really say, okay, this is an interesting class.
let's thank the speaker again.